Hello and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 93,000 computing professionals and students who are ACM members. I'm Will Trace, Lockheed Martin Fellow Emeritus, former chair of ACM SIGSOFT, and a member of the ACM Professional Development Committee. For those of you who may be unfamiliar with ACM or what it has to offer, here is more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in a constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen now. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including Communications ACM and Q. Access to the ACM Digital Library, the world's most comprehensive database on computing literature. International conferences that draw leading experts on a broad spectrum of computing topics. And support for education and research, including curriculum development, teacher training, and the ACM Turning and ACM Prize in Computing Awards. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, for those of you joining us for the first time, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically through the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slider audio, press the F5 key in Windows or Command-R if you're on a Mac, or refresh your browser on a mobile device. Or you can simply close down and relaunch the presentation. Control volume, adjust the master volume on your computer, and most importantly, if you have any questions during the webinar, please type them into the Q&A box at any time during the webinar and click on the Submit button. It's my job to organize the questions and ask Grady, and he'll reserve time at the end of the presentation to address them. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available, and please check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open on your screen. Please take a minute to fill it out and help us improve our webinars. You may also open the link to the survey at any time from the resources window on your screen. Also, I'd like to point out that you can use the Facebook and Twitter widgets at the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag #ACMLearning. We also have a new community discourse page to continue the discussion after the webcast, including questions we won't be able to get through during the presentation. Today's presentation is The History of Software Engineering by Grady Booch. Grady is the Chief Scientist for Software Engineering at IBM Research, where he leads IBM's research and development for embodied cognition. Having originated the term and the practice of object-oriented design, he is best known for his work in advancing the fields of software engineering and software architecture. A co-author of the Unified Modeling Language, UML, a founding member of the Agile Alliance, and a founding member of the Hillside Group, Grady has published 6 books and several hundred technical articles, including an ongoing column for IEEE software. Grady is also a trustee of the Computer History Museum. He is an IBM Fellow, an ACM and IEEE Fellow, and has been awarded the Lovelace Medal and given the Turing Lecture for the BCS, and was recently named an IEEE Computer Pioneer. He's currently developing a major transmedia documentary for public broadcast on the intersection of computing and the human experience. Grady, without further ado, take it away.
Thank you. Trust is an interesting element of every aspect of human interaction. We trust our families to love and take care for us. We trust our nations and our governments to act in our best interest and to use the resources to which we've given them in efficient ways. Trust is also important in the various ways we go through our days. We trust that the bridge we're crossing is not going to fall down upon us. We trust that the oil in our car and the gas in our car is properly mixed. We trust even when we go in and have our hair fixed that they're not going to use strange chemicals on us that will render us hairless. And by the way, that's not what happened to me. That's another long story. Curious thing about those latter three is that institutionally it requires a degree of training, an apprenticeship, and in all those cases licensing to be able to do those kinds of things. And so this is, at least for the first two, for civil engineering and chemical engineering, what the role of an engineer is all about. The picture in the upper right-hand corner is a curious one because, strangely, in many states in the United States, you have to be licensed to braid hair and have to have gone through apprenticeship and done several hours of training. Curiously, this is not true of our software-intensive systems, and that leads us to what software engineering is all about. Let's begin with the nature of engineers. Imhotep is probably the very first engineer, and he had the absolute coolest job title. Imagine putting on your business card, "I am high priest to the sun god Ra." We consider him an engineer because he apparently engineered a number of the early pyramids. And, well, apparently he did it right because he managed to survive. As we move forward in time, the way and the role the engineer played in society had some degrees of checks and balances. In the 19th century, the Count of Hamabari said, basically, if you build a building and it collapses and you kill somebody, we're going to put you to death as well. Now, this is pretty harsh, but it's a good example of checks and balances in the law. We trust those who build things for us to build them well, and if they don't, there are indeed consequences. Ismail al-Jazair is another candidate for being the first engineer. He was in Turkey at the height of the Islamic Golden Age, and he was part of a movement that built these amazing mechanical devices. His book on the Book of Knowledge of Ingenious Mechanical Devices inspired many generations to come. In fact, there was a renaissance of those ideas in the Victorian era. He's also considered the father of robotics. Well, as for engineering as a discipline, strangely enough, it's a fairly new field. The very first licensed engineer was a gentleman by the name of Charles Bellamy in, of all things, the state of Wyoming in 2007. Now consider all the amazing things that had gone on in the Industrial Revolution prior to 1907. You think of the railways, the steam engines, the boilers, the steamships, the bridges all made, and those were done without licensed engineers. So we had a long period of time, millennium, in which structures in which we trusted and depended were built by people that were, in a way, citizen scientists. Why was it becoming important in 2007 to license these folks? Well, this is an issue of following the money to a degree, because in that era there was a tremendous amount of mining going on, issues over water rights and rights of way, and the building of bridges with new materials. And because of the failures that existed, there was a desire to have degrees of accountability. So Charles was the first, and there are many that followed. That being said, that did not mean the field was perfect. We see, for example, on the bottom right, there still were many explosions of boilers around the time because standards weren't quite in place. We hadn't quite understood best practices. In the upper right, we see the aftermath of the St. Francis disaster, a dam built by Mulholland and was in fact poorly engineered. Although built by an engineer, it did have failures. But this is the nature of engineering. It is a process of applying science, applying it in the world, and learning from those kinds of failures. While there were many specific instances of engineering for particular fields, there were also interest in looking at systems that involved many disciplines, and thus the notion of systems engineering came to be. Really, it was in something that came out of the Bell Labs in the 1940s, in the fog of war, as we begin to see all these disparate industrial activities come together to build systems. INCOS today is the society that manages that. But I want to focus upon software engineering. Engineering, by and large, is what we call an occupational closure. And what that means is that it is intended to be designed by those who are in the industry, both as a way to validate people who we declare, yea, verily, I am X, Y, or Z, and also to, in some ways, exclude people that don't meet those criteria. So it is in software engineering. In some states and in some countries of the United States of the world, you can declare yourself a software engineer and nobody will care because it doesn't fit under the rules of that country. If you're in Canada, for example, or if you're in Texas or any number of places, then in fact to call yourself an engineer of any sort requires a degree of licensing. So in the software engineering space, we're in an interesting place. We are certainly by no means as old as civil engineering, not as old as electrical engineering. We're just at the beginning of defining what engineering is all about. So let's turn to our field in particular. And speaking of its newness, the first computers, in fact, the first use of the word computer in the sense we know it today, were speaking of computers as women, and most humans, and most of them were women, in fact. We didn't even have the term digital that was in wide circulation until around 1942. This is when George Stibitz was taking his ideas from George Boole, and applying them to electromechanical devices. In fact, it wasn't until 1952 that the term software was coming into wide circulation, and this was devised by John Tukey around that time. So we live in a very, very young discipline in many ways. So it's no surprise that software engineering is just at the beginning of the beginning. In fact, where did that term come from, software engineering? Well, many believe it came from the NATO conference on software engineering held first in 68 and 69, and it was Frederick Bauer who proposed it. It was meant to be a provocative title, saying we're dealing with the engineering of systems that are software intensive. Turns out that wasn't true. As it turns out, in 1966, there was an article by Anthony Odinger, who happened to be one of the early presidents of the ACM, and he wrote a letter in CACM that used the word software engineering. And he was trying to make the distinction that at that time, yes, there was science, and yes, there was computer science, but what we were doing is something different. That wasn't the first instance of the use of the term software engineering. In 1965, if you look at the literature, you'll find that there was a large body of companies that were doing electrical engineering and computer engineering, and a few that proclaimed they were doing systems software engineering. In fact, this is the first instance we found of that. So one might claim that maybe software engineering was first found in an ad. Well, all the data I have points to Margaret Hamilton as being the person who coined the phrase software engineering. At that time, she had worked on the SAGE program. She was then the lead developer for Skylab and Apollo, and was working at Draper Labs. And around that time, in 63 or 64, according to an oral history that she recently did, that appears when the term first began to be used. So we can speak of Margaret as the inventor of the phrase software engineering. It's interesting then, because I said earlier that the first computers were women, meaning the first computers, those who compute, tended to be those who were the ones who did the computation themselves. And we're coming back again to the influence of women in early ages of computing. Well, is software engineering an art or is it a science? Grace Hopper suggests that in many ways it's a practical art, whatever that means, certainly a sense of engineering. Edgar Dijkstra observes that it's also an art, especially if we think of programming, because it deals with the art of organizing complexity. And Don Knuth even describes computer programming as an art because of this notion of focusing upon producing objects of beauty. I think all of these things are true, although I like what David Parnas has to say, that there is a distinction of computing science and the other stuff that we do. This is like distinguishing chemical engineering and chemistry. Both are valid. Both have their particular sets of practices. And just as in chemistry, so it is true in software engineering. we have computer science, we have software engineering, and those two are different. Software engineering is indeed an art and a science. It is the art of the practical. I think of it this way. Engineering is always about the resolution of forces. And so if I'm a chemical engineer, I'm thinking about the things that go on within a reaction. If I'm a bridge engineer, a civil engineer, I think about the static and dynamic forces. So it is true in software engineering, that if I'm building a software-intensive system, these are the kinds of things that I must weigh against. And every project varies, every point in time varies, every domain varies. And so we may come up with some of the best practices for the field itself, but we have to apply those as engineers to the specific time and place and culture in which we're developing. In some circumstances, if I'm a young startup trying to build the next biggest really cool app, then, my main forces are upon things like, can I even build this? Can I scale it? Is it going to be secure? On the other hand, if I'm building something like a pacemaker or algorithms for injecting genetically modified genes into some human, then legal and ethical issues might play a role. If I'm building systems of scale, issues of cost and schedule come into play. This is why very much this is an engineering discipline. Brian Selleck, I think, observed something else interesting about these best practices, that while your mileage may vary, one of the things we do know about the good engineering practices that we've seen thus far in software engineering is it fits a pattern. There are periods of discovery and invention and implementation and some degree of regularity that takes place. Now keep this slide in mind because we're going to see that appear again and again being reinvented as each age discovers some new truths about software engineering. All right, let's dive into the hardcore history of software engineering. And we actually have to begin all the way back to the days of Charles Babbage. So why do I start there? Well, we didn't really have software at that time, but it's interesting as we go through these various periods to look at the interplay between science and the actual delivery of these kinds of systems, because the two have this wonderful dance between them. We learn from the science, we build things. From building those things, the science itself advances. We can think, therefore, as Ada Lovelace is really the first person to get in their heads that programming was a thing unto itself. And so in working with Charles Babbage, who was at that time, he built pieces of the difference engine, was thinking about the analytic engine, she had this most remarkable insight that with something like the analytic engine, there was an activity of algorithmic development, the notion of programming itself. So she's perhaps the first to have these neurons fire, saying this is something wonderful and different. George Boole similarly brought a new way of thinking to the mathematicians of the world, taking the ideas of just raw logic, Russell and Moorhead and those folks, and saying, hey, can we apply these kinds of ideas of basic logic to the laws of thought? In fact, that's what the title of his first book was. So we began to see a different way of thinking from what the previous life had been. Now, I mentioned that the first computers were women, and this became especially manifest as you turn toward the middle of the 1800s. You're looking here at a picture of Pickering. He's in the left-hand side of this, and his computers. Why are they called computers? Curiously, the astronomers felt it beneath them to go off and do these laborious mathematical calculations. And again, it's an economic issue. They didn't feel it was worth their time. So they delegated the mathematical computation to a set of, in this case, mostly women. It was low cost for them to do so. And Annie Cannon and Henrietta Leavitt were two of those that were part of the Pickering group. And what did that mean to be a woman computer? So again, you have a set of people who were probably the first to experience what does it mean to have a rigorous process, to take some mathematical specification, to take some amount of data and actually act upon it. So in a number of ways, Pickering's group, led by Annie, were beginning to manifest themselves as very organic computers. And so the ways in which they organize their teams have echoes or reflection today. In fact, some of the echoes of agile development you see reflected in what Annie and Henrietta were doing. Again, a different way of thinking. As problems began to scale, and now we're toward the late 1800s, early 1900s, and the degrees of automation were possible that we actually begin using mechanical calculators, there was further regimentation that took place. And in fact, a very common structure you would see in these computers, again, physical people, is that data would enter one physical row, a person would calculate it, they'd pick it up, put that results of it in the inbox next to them, the next person would pick it up. We have a pipeline architecture. And so, again, the manifestation in organic humans of a process which we eventually were going to make manifest in software began to be applied here. Now, this is where we start seeing the interplay between computing and other kinds of disciplines. Frank and Lillian Gilbreth were deeply involved in time and motion studies in the early 1900s. They of the Cheaper by the Dozen fame. They had a dozen kids, and there were some plays and books written about them. They had this notion that there was a way to codify those processes in a thing we call process charts, which happened to be a predecessor of flow charts. Edith Clark, who was the very first woman to get a degree in electrical engineering, also began to write about the process of taking mathematical specifications and turning those into reality and results. So much like what Gilbreths were doing, she was doing this in her electrical engineering progress. Again, not fully stabilized, but we're kind of there in terms of a process. As we begin to mechanize more of these things and punch cards came into play, then there was a further institutionalization of the process of developing computing systems. So Gertrude Blanche at the time was head of the Mathematical Tables Project. Fascinating project. This is, again, at the height of the Great Depression. There were many people out of work. The Work Projects Administration had funded a number of efforts to keep people employed in meaningful ways, and one of those was the Mathematical Tables Project, which was an attempt, predecessor of CRC tables, by the way, which was an attempt to take mathematicians and other folks to go off and build things under government funding that would be generally useful. And this required tremendous amounts of computation. She, much like what you saw in the earlier ages, was the person who led most of the computers and began to establish the processes which we eventually automated in full that we now see today. J. Presper Eckert, a name that will pop up again and an important name in human computing and later computing, wrote an important book around that time called Punch Card Methods. And you can think of this as the first methodology. It was, in a way, a pattern language. If I'm going to solve problem X, how do I organize my punch card machines to do that? What are the trade-offs? What are the efficiencies? What are the risks associated with it? So he began the first methodology, if you will, of software-intensive systems. Again, we're still not at the period where software was a thing unto itself, and so we now turn to the age in which we begin to mechanize these things. This is around the time of Stibbits. Remember, he was inventing around this time the idea that digital was in fact a thing to distinguish it from many of the analog systems that happened in that time frame. Stibbits had the notion, again, a different way of thinking, that relay logic was a way to take Boole's ideas and transform them into the hardware we have. This is also the time that John von Neumann began to introduce new ways of thinking about computation. And it was through von Neumann's interaction with Aiken and Goldstein that led to Aiken producing the first degrees of electromechanical computation. So again, we see a shift in the way of thinking. It wasn't just a matter of doing these mathematical calculations out there with our machines, but it was rather bringing those calculations into the machines themselves. Grace Hopper, about the same time we had the notion of software treated as a word unto itself, had this incredible insight that it was possible to devise languages that were independent of the machines themselves. So in a way, she was the first one who had to do abstraction. She had the insight that we were building all these one-off special purposes machines, and yet the algorithms we were doing to apply to them could be independent of the machines themselves. Again, a different way of thinking. And now, in the fog of war, in World War II, we enter two parallel universes in which the discipline of engineering emerged parallel, and there was sort of an interplay between them that didn't come back together until the Cold War time frame. We're looking at the Colossus. And so here we are at the height of World War II. Alan Turing, with the bomb and the tunny, had given us some of the foundations for taking the ideas of computation and making them mechanized. But again, it required the insights of an engineer, in this case Tommy Flowers, to take those and say, my gosh, these things can be programmable. So combine what Tommy had done with what Grace Hopper had done, and all of a sudden we see the emergence of software as a thing unto itself. Dorothy DeBoyson was again, the human female computer that was the primary operator for the Colossus. She led the team of women who ran the Colossus itself. And so she began to codify the ideas of workflow that eventually we put in the machines themselves, but now is done by the humans. In a parallel world, we also see Konrad Zuse. And if in a different time and place, Germany would have been the center of gravity of modern computing, because he invented the first higher-order language. He invented the first general-purpose stored program computer, but in many ways that turned out to be a cul-de-sac because of him working in Germany and, of course, all the fog of war that led there. Now, the parallel thread was happening in the United States, and this is with what came about with ENIAC and the programmers here. So again, we speak of these women programmers. In fact, let me go back to the slide. What did it mean to program the ENIAC? Literally, it meant programming these plug boards. So there's some great histories and oral histories of many of these women. But if you study what they've done, they'll say what happened is that the mathematicians would come to them saying, hey, we want you to go set up the machine to solve this particular ballistic problem. They had no further direction. So they would come together in a corner, figure out what is the right process, and literally begin to program the computer. So in a way, they were the first electromechanical programmers. Now, the ENIAC was not a stored program computer until later. The stored program was effectively these sets of women taking the plug boards, plugging them in, and then that was the program itself. The next program, they'd pull them out and do it again. So they became, in a way, the operating system for those machines. Now, at the same time, there was work going on, and this is again sort of end of the war, beginning of the Cold War. We saw the emergence of some best practices from the computer sciences saying, wait, there's something there that allows us to treat our machines very, very differently indeed. Tom Kilburn brought us the notions of, with Whirlwind, that there was the opportunity to do real-time kinds of programming. Wilkes and Gill brought the notion of subroutines, so taking further the idea of abstraction. The importance of this is now we had a new vocabulary with which to build our systems. J. Presper Eckert and Mauchly also, in their later machines, began to realize that software was a thing unto itself. And it really then became, in the post-war time frame, that software and what it was became a discipline by itself. In fact, it was John Backus who took the ideas from Hopper and others and those kinds of languages and said, wait, we can actually build a higher order languages that takes those mathematical things and deals with the tedium below it. And so thus was born Fortran, the first meaningful imperative language. Herman Goldstein, based upon some of the things he saw from Gelbreth and others, along with John von Neumann, produced a formalism for what became flowcharts. And now all of a sudden we had an interesting tool, a tool for describing our systems in terms of the flowcharts as a language for us above the programming language itself. Now, those were mostly scientific and military kinds of applications, but we began to see the emergence of computing for commercial uses. In fact, the very first commercial computer was Leo for a tea company in England. And this is where we began to see software as a component. In fact, it was John Pinkerton who had the insight that on the machines he was building, there were many things that we would do over and over again, and those began to be bundled up into libraries and in ultimately operating systems themselves. Grace Hopper influenced the creation of what became COBOL. Robert and Gene were important pieces of it, and those three and others led to the creation of another imperative language, giving yet another tool to the software developer themselves. In fact, we begin to see the institutionalization of software reuse, not from a particular person, but from an organization called Share, as we saw a multitude of IBM computers in particular enter the marketplace. People were finding these components that they used over and over again, and Share was established as the mechanism to literally share those things. The next big bump in what was going on, and this had incredible influence upon all that followed, was again woven on the loom of sorrow, the Cold War, and that's the SAGE system. So consider in that time frame the threat was Russia. We were worried about in the United States that Russia would send bombers over the Arctic, and so we built this huge set of systems that watched over them and gave us a command and control system for us. Well, this is again where Jay Forrester began to bring the ideas that it wasn't just symbolic models of computation that were possible, but there are other ways of thinking in his ideas of what whirlwind, which then led into the SAGE system itself. Bob Evans was the leader for SAGE. Christopher Strachey brought us the ideas of time sharing, and those two together were starting to establish a very different way in which software itself was created. We saw Diana St. Johnson begin to manifest that self in businesses. She was the first person in the UK to actually establish a software services business that then treated software development as something you could outsource to another set of people to go off and do this. The other important thing about the SAGE project it was big. It was both a system of software and hardware, and it was the largest software-intensive system people had built at the time. And this led to what we called the software crisis, because it was very clear to those people inside the system that our machines were becoming more and more powerful, and yet we were in the programming priesthood, as some called it. There simply weren't enough programmers around to do what we're doing. Again, look at the economics of it, because here is a time frame in which the machines were still far more expensive than the humans that programmed them. And so the institutionalization of what I spoke of as the programming priesthood, which is a phrase that was used around that time, in which you would have the machines off in some very protected room. The programmers would be elsewhere. Because the machines were so expensive, you couldn't be with them all the time, and so you would labor as a group unto yourself. You'd use your flowcharts, you'd use your programming templates, you'd carry those over to your key punchers who would do it, send it to the machine, and get back the results. Very, very much a batch-oriented process. And Chris Strachey's ideas of time sharing didn't really apply until those machines became less expensive for us. Well, this is where the ideas of project management for software engineering came into play. Fred Brooks, of course, is a quintessential example of this, because he began to understand that software engineering was not just a technical process, but it was a process associated with humans as well too. Now, we begin to see ideas from academia come into play, saying, wait a minute, we can apply some of the things we have learned in terms of these structures you're building in software, and there are ways to approach it. And so Larry Constantine was perhaps the first to introduce the ideas of modular programming, the ideas of coupling and cohesion, saying that with languages that were algorithmic in their nature, there is a way to decompose them that helped attack that complexity. Edgar Dijkstra, therefore, began to institutionalize those in very formal ways that again gave us a different vocabulary for the software developer, a vocabulary for the software engineer, the idea of structured programming. At the same time, there was an interesting thread going on that didn't really manifest itself pragmatically until later, first informalisms, Robert Floyd and Tony Hoare in particular, began to realize that the structures we were building indeed had some formalisms associated with them that maybe we could prove program correctness. And so here is an attempt to take the ideas of true science and put them into the engineering of software. O.J. Dahl and Kirsten Nygaard had an outrageous idea, outrageous at the time, that was saying, wait, our imperative languages are interesting, they're algorithmic based, but there's another way of looking at it. So we'll come back to them because they had laid the seeds in the mid-60s for things that were going to become important later. So consider where we are at this point. We have, in the software world, software-intensive world, we have large machines, much more expensive than the humans themselves. We can't build these software systems fast enough. We have primarily algorithmic languages, and the main problem we face is we can't build software systems fast enough and of good enough quality, and furthermore, our complexity is rising. Enter Margaret Hamilton, because she came to us in a particularly interesting point in history. Here she was working in the 60s in the space program, very software intensive. We learned a lot of things from SAGE and other kinds of systems and commercial systems, but she brought the notion that there is an engineering process that makes sense there. You can read this from a particular interview she did, but it points out that the mindset she was working in is that she was building systems of which software was an important piece of it, and the software could and should be managed just as deeply as all the other hardware pieces of it. Well, now we moved into an era where all of a sudden the machines started becoming less expensive than the programmers themselves. And we had a flowering of ideas in software engineering. In many ways, you could think of this and the next set of slides as the golden age of software engineering. Win Royce brought to us the notion of software development. Now, he is much criticized for what the waterfall process is. But if you go back and read to what he has done, you realize he was talking about iterative development. He mentioned prototyping. It wasn't as rigid as its critics might be. He laid the foundations for what we do today. Wirth brought the ideas, building further upon Larry Constantine, not just of separation of concerns, but also a stepwise refinement. Add that together with David Parnas's ideas of information hiding and Barbara Liskov's ideas of abstract data type, and all of a sudden we have a new vocabulary for the software developer. From a very different set of cultures, the data modeling world, Peter Chen then brought to the table the idea of entity relationship modeling. So now we had this rich primordial soup of ways to express the artifacts and components of our software engineering systems. And that therefore led to the first generation of really fundamental software engineering methodologies. Doug Ross's SADT, Larry Constantine structure design, Ed Jordan structure design, Michael Jackson structure design, Tom DeMarco structure analysis. I would have included Chris Gain and Trish Sarson in their work, but my gosh, even my Google foo skills did not uncover a single picture of either of those two. So if any of you have one, please let me know, because they were also an important factor in this time frame. But now we begin to see the creation of a process that defined the way we built software-intensive systems. At the same time, we began to see the edges of those fit into play as well. Michael Fagan brought us the ideas of software inspection. John Bacchus threw in the ideas of functional programming, which came to be later. Leslie Lamport started the ideas of the rules and best practices of distributed computing. Again, each of these giving us a different vocabulary for the software engineer. And then, of course, following on from the microcomputer, the mini computer, period of roughly a decade or so, this led to further changes in the kind of systems with which we interacted. And again, the systems we built were now vastly less expensive than our humans. We're now in the microcomputing age. This was the flourishing of the second generation of methods, bringing together the ideas from Nygaard and others in object-oriented programming and abstract data types into what became the unified modeling language. It had its roots, back in my earlier work in '86, Jim's work in the 90s, Ivar Jakobsen's idea of use cases. of use cases as well. And the three of us came together in an interesting history unto itself that led to the standardization of the UML in '97. Here's a great example, too, of where you found industry banding together and then eventually making it what it became, in effect, open source. At the same time, this was a tremendously vibrant time in the software engineering community. We had Stephen Meller with his object-oriented ideas, Ed Jordan again, Rebecca Wirfs-Brox in responsibility-driven design, Pete Code, and many others who were playing a role in each adding some of the best practices we knew. But we also began to see the other aspects of software engineering come into play. Barry Bame's work in economics and his revised model of process, the spiral model. Vic Basili in his ideas of empirical software engineering. Brad Cox is an interesting one because if you think about Brad's influence, he eventually went on to produce Objective-C, which had tremendous influence upon Next and Apple. He had this idea of component-based software engineering, and it's those ideas that ultimately led to the IBM SOAM model, to Microsoft's Olay and COM, and the beginnings of what we'll see pop up again in component-based engineering. Harlan Mills and his ideas of clean room software engineering, and of course Watts Humphrey and his ideas of the capability maturity model, saying there's a way to measure the maturity of processes themselves. Well, and I should also mention James Martin, who came from, again, a different culture, mostly the commercial side of it, and John Zachman as well, the business side, leading together a really interesting primordial soup of ideas in the space. This is where we also began to see those ideas begin to manifest themselves in very concrete ways. In the UK, the best practices of software engineering processes were brought together in SSADM and a standard for the UK. Similar in the US, we had the Defense Systems Software Development Standards. The formation of the Software Engineering Institute itself was an indication that there was economic value in treating software engineering as a viable study of framework. And much like the direction that Zachman and James Martin were in, the business engineering side of it, the enterprise development side, led to organizations such as TOGAF. Well, there are other folks who contributed to some important elements of software engineering that, again, pop up as we'll see later. Don Knuth's idea of literate programming that brought together the ideas of taking very clear, structured ways and putting those in the code itself, leading to the phrase that I and others have said, that the code is the truth, but it's not necessarily the whole truth. Richard Stallman brought the ideas of free software, which, as we'll see, influenced later on the way we build software-intensive systems. And then Alan Cooper, with Visual Basic, brought yet another vocabulary to the world, the idea of visual programming as a way of separating ourselves from our languages and actually doing it in very visual ways. This, in fact, was one of the things that inspired the model-driven development stuff later on. Well, again, the world shifted out from under us. With the advent of the ARPANET and then the Internet, the world changed. And we saw the change in our software-intensive systems do so as well. The first ideas of Scrum were laid in '95, in many ways reflecting this interesting gestalt between the open source community, between the beginnings of the Agile ideas, and the ideas of distributed team development across the Internet. Kent, in his work with Ward Cunningham, led us to the ideas of extreme programming, which he first described in '96, and Martin Fowler, a few years later, brought the notion of refactoring as a vocabulary for us. Many of the practices that we had done on the rational side came to fruition in around 2000 when it became an open standard as well. There are also some other people that played important parts in the vocabulary of software engineering. The Gang of Four in particular, Eric Gama and crew, began to give us a different way of thinking about levels of abstraction. In fact, this was semi-formalized in the formation of the Hillside Group in '93, where the patterns community really came together. Philippe Krusten and Mary Shaw in particular brought the notion of software architecture as an important element of the vocabulary. In fact, this became ultimately manifest in an ISO standard. At the same time, just like in previous generations, we saw work going on in not the fringes, but the edges of methodologies themselves. Now, you may say, why is that Netflix guy showing up here on this? Interesting history behind Reed, that prior to being CEO of Netflix, he was CEO of a company called Pure Atria, which was a configuration management tools company that Rational acquired back in the day. And so the earliest commercial products for configuration management were actually done under Reed, of all things, and he went on to bigger and better things inside Netflix. Eric Raymond further institutionalized, especially in the legal mechanisms, ideas of open source. And then we saw an interesting other economic development, the move toward outsourcing. Again, follow the money is an important element of looking at the history of software engineering. And Kiran was a gentleman working in India who established the first major outsourcing contracts between General Electric and India, and we began to see the foundation laid for distributed development, which had an important economic and practical impact for how we build our software-intensive systems. Well, then, of course, mobile devices hit the scene, and the world changed out from under us. And so we saw the beginnings of things such as Git and GitHub later on. Why is this important? Because, again, it's a vocabulary, a mechanism whereby people actually built their software-intensive systems. Jim Copleen took the idea of patterns and applied it to organizations themselves. And much like what we saw the earliest human computers doing in terms of looking at the world in different ways of thinking, Jeanette Wing finally began to institutionalize those things in her ideas around computational thinking. Now, and then there was Joel Sapolsky and his colleagues in building Stack Overflow. Where does this fit in software engineering? It represents part of the culture of the way software was being developed by a large open source community who was sharing in ways that were unprecedented. And finally, around the time Robert Martin brought us back to the ideas of Don Knuth and his literate programming, and observing that those same practices apply even in our modern approaches today. Well, again, the world shifted, that in the presence of distribution, the next thing we saw happen is these consolidation of activities into the cloud themselves. And that changed the way of software development. And all of a sudden, we had new vocabulary in the form of what we would call DevOps. Andrew and Patrick were the ones who led the ideas here, and the notion of a full stack developer came into play. So we began to see that software engineering all of a sudden was addressing issues that had many different views associated with them. It wasn't just the software pieces, but it was the context of those software pieces within the distributed systems in which they were working. The next thing that happened is that within those cloud systems, we began to see the ideas of Brad Cox come into play, forming these islands of componentized structures. And thus, component-based development from his work further on led us to service-oriented architectures, the rise of APIs, and the growth of these islands within the clouds themselves. And therefore, for that reason, I include Jeff Dean as an important influence, because through Google, he began to establish that as the new operating system of the age. And similarly with Jeff Bezos, the idea of platform computing and cloud computing with what he did with Amazon. And here we are today. Now, this is a slide that at first may look like there's no software here. And that's exactly the idea, that we are in an age of ambient computing, where it used to be the case our software-intensive systems were out there, but now they are inside here. We live within them, and they all surround us. And this is as it should be. When I cross a bridge, I don't think about the engineering that takes place. I just cross the bridge. And so it is with software-intensive systems. I go through my day touching a multitude of software-intensive systems, and I must trust them. This is the state of software development now. So let's step back for a moment and see what the lessons learned we can make, and then project out for what might happen. There's a pitch I've often covered, which takes longer than I have now, that looks at what separates us from our vision in terms of turning that into raw running systems, this ladder of physics to algorithms, architecture, and so on. Computer science is largely focused upon issues of physics and algorithms. And software engineering covers a broader spectrum, moving from algorithms to architecture to organization to economics and the human issues. The ethical and moral issues come to play within our world very much so. We've begun to institutionalize those in a thing called SWBOC, first written in 2004, current version is 2014. I think it's a good start. Is it perfect? By no means. We have a way to go. It codifies things in terms of software development in these particular areas, but here's the warning. This applies, we always build systems that help us fight the last war. And in many ways, what we know about software engineering today is fighting the last war. But just as you saw in the history thus far, there are things that are changing out from under us that are going to change the very assumptions upon which these ideas are built. The systems engineering body of knowledge, INCOS has done this, follows very much the ideas of the SWBOC as well, saying there are things we know about how to build these systems that we could actually codify as rules. And that's a good thing into our world. Let's see, here we go. All right, so if I were to step back and look at the entire multi-decade history of software engineering, if I look at it from the point of view of the domains, we can see a move from mathematical domains to work on symbolic computation, to things that were more personal in nature, to systems that were distributed and connected, to those of what we call imagined realities. And I'm not just talking virtual reality and augmented reality, but it's building worlds in our software-intensive systems that are worlds unto themselves. I go into my games. I go into my phone. They become my own world itself. In many ways, software engineering has addressed the problems of that time. We laid the fundamentals of software engineering in the early mathematical days that were the problem of what's the basic vocabulary of software? The symbolic era was when we were dealing with managing complexity. Human-computer interaction came into play where the economics of computing changed such that they now became very, very personal. In the last few decades, it's been a matter of managing scale, but to now, as what we've seen with Facebook and others, the clear and present task of software engineering also touches upon ethical and moral issues. There's another way to cut this as well, and that's one of scale. There are many systems, like in the lower right-hand side, that are doghouses, that I don't need any of the stuff that I've talked to you about. I just put a few people in a room, go off and slam out the code, and I'm done. But as the risk and cost increase, then I'm going in counterclockwise order, then all of a sudden I need to apply more discipline. And finally, we're at the level of where we are with cities. Most software development is like engineering a city. It requires changes in the presence of established systems. It requires trust with systems that I have no control over whatsoever. It's the antithesis of greenfield, but as software has moved itself into the interstitial spaces of our world, software development, software engineering is much more like engineering new cities themselves. Well, this is where the future lies. And I alluded to the notion that the world is changing out from under us, and that's what's happening with AI. So the foundations of artificial intelligence have been around for literal decades. In fact, you can go all the way back to Turing and see some of the ideas of computation as a thinking process and how to make it manifest played a role. But today we see a little bit of a dichotomy in that there are symbolic approaches to computation, traditionally the things I've talked about here, but also connectionist models of computation, meaning the ideas of deep learning and what DeepMind and Google have done in this space. So the question on the table is, will this fundamentally affect the software development process? Well, let me approach that in two ways. I work in this space now, and if you talk to many of the people who are working in that space, you realize there's still a lot we don't know how to do. We don't know the best architectures for our neural networks. We know some of them themselves. AutoML is an attempt to apply machine learning to the process of building architectures themselves. But by no means can we claim that artificial intelligence has rigorous specification and testing. It's still much more an art. So that field itself has a ways to go. At the same time, will it impact software development? My take on that is somewhat. That for the conceivable future, we're going to see the orchestration of AI systems together with traditional symbolic systems, and that's going to begin to change the way we look at how we test and integrate these things, because now we're dealing with systems that no longer do I program, but I teach them. And so much like in the earliest days of software engineering, I have a new vocabulary that the generation today will need to struggle with to say, how do I incorporate the best practices thereon? One thing I do know is that no matter the medium we have, the fundamentals always apply. And I think this is true, be it an AI system or a non-AI system. Abstractions we know are important. Having a clear separation of concerns, a balanced distribution of responsibilities, and simplicity. These four things seem to echo across the decades of every one of the pioneers I mentioned here. And in terms of process, we know this to be true of physical processes as well. The work from Herbert Simon and others prove this to be true. We should grow our systems in incremental kinds of ways. But there's work to be done. And so for the next generation of software engineering, I think these are the tasks that are ahead of us. How do I orchestrate symbolic connections and quantum models of computation? Where does the pendulum lie in terms of architecture? Is it a lot of upfront design? Is it a little upfront design? Where should it live? The pendulum is swinging also in terms of edge and cloud. Today it's swung to everything is out in the cloud, but we see it beginning to swing back to moving it on the edge itself. And again, that changes the vocabulary of engineering. And lastly, scale becomes still a continuing problem for us. How do I build systems with untrusted components that are part of considerable legacy, of considerable inertia, and they're dealing with the general public? So this is again why issues of ethics and morality come to play. The phrase I often use is that every line of code represents an ethical and moral decision, and I think that is true even more so now. Well, let me wrap up. This is what excites me about this field, that there is so much that is yet to be done, so much that we have changed the world. And believe me, if I had another hour, I'd tell you of a dozen or 24 more people who are involved here. These are only a few of the names who have influenced it, but literally thousands upon thousands of people have contributed to what we call software engineering today. And you out there are the next ones who will make it manifest. I think of it this way. Software is the invisible writing that whispers the stories of possibility to our hardware. Invisible writing that whispers the stories of possibility, and you're the storytellers. And software engineering is the discipline that helps us build systems that are trusted, that people beyond us, beyond our creations, can trust in. So thank you. This is a great opportunity. Will, Jan, thank you for the opportunity to come here. Here's how you can reach me. Every time I gain a new Twitter follower, an angel gets its wings, so feel free to follow along. And Will, maybe we have time for a few questions?
Oh, we have time for a few questions, and I'll just say I would thank the audience for their attention and for the plethora of questions that have flooded in, but I'll just have time for a few. The first one is, what do you see as an influence of regulation, ethics, and licensure on the future of software engineering? You touched on it a bit, but could you elaborate?
That's a great question. I'm honestly uncertain, unsettled on the issue of licensing, mostly because I think it is inevitable and desirable. As any field matures, we need to have some way of saying, yea, verily, I know that this system was built in a meaningful way. But at the same time, I know that we struggle with even the basics of what the best practices of software engineering are. And so while I think licensing in the grand scheme of things is inevitable and desirable, we're a ways from it because we don't yet know what we would license people against.
Thank you. Here's what impact have professional societies played in influencing software engineering?
Great question. I am a member of IEEE and the ACM because I believe in the power of those organizations to be important voices to give a forum for ideas, to act as a group that I trust that can lobby on the part of best practices that we know in this space, to provide a vehicle whereby good ideas can rise up and be discussed well. So I think that those professional organizations are an important way to help us build a lasting profession of software engineering. In many ways, there are parallels with the guilds from the Middle Ages and later on to what we see with the IEEE and ACM. They are the places that like-minded people can band together and help define what is it are we all about. So yeah, I think these institutions are absolutely important for us.
Okay, time for one more question. How essential is research in theoretical computer science to the advancement of software engineering?
Great question. So you'll notice that in many of the people I mentioned, somebody might say, well, they're not software engineering people, they're just computer scientist kind of people. Absolutely, is the way as it should be. In engineering discipline, you see a healthy dance between the pure science and the pure engineering of the systems themselves. I speak of it as a dance because the science is vacuous unless I bring it into reality through engineering, and engineering is unfounded unless I can build it upon an establishment, a strong foundation of science. And so the two work very, very closely with one another. If you look at the golden age of software engineering, if you will, there was this wonderful interaction between the people working in theoretical computer science and software engineering itself. I'll give you one example that I was unable to mention here. There was some interesting work going on in what became aspect-oriented programming. The idea that there was a new way of looking beyond patterns that were kind of cross-cutting concerns. And there are a number of computer scientists that were trying to make those ideas manifest. So there's an example of a really healthy interplay between the theory and the pragmatics. Now, turns out that never really fully flowered, but gives you a good example of where those ideas can take root. So yeah, I mean, I'm in IBM Research, which is the place we try to bring science and engineering together to build these things. Without the two, then, you know, that duality is important. It's absolutely essential. Great question.
Okay, I'm going to squeeze in one more clarification. Could you talked about the pendulum swinging between edge and cloud computing. Could you just sort of clarify what you meant there?
You bet. So what I mean by that is there was a time that computing was always in the devices right beside us. And that eventually moved out to the data center and eventually to the cloud itself. So today, if I do any degree of computing, it's actually happening out there. But with the rise of computational resources in our devices, where I can now put on my next generation iPhone, where I have an inference engine, for goodness sakes, where I can begin doing computation there, all of a sudden it moves the computation away from the cloud and out in the network to my local device itself. And that changes the vocabulary with which I interact with the system. It changes the degree of interaction. It changes latency. It also has tremendous implications for privacy, because now I can guarantee to a degree that certain things only happen within the control of my device itself. Microsoft has telegraphed this, because if you look at their current direction, they're investing tremendous amounts in edge computing because the devices have this degree of computational power. That changes the way we think, because if you go down the path of Bezos and Dean, you sort of construct systems full of these APIs. You know they're out there. You don't care about them. But edge computing, the pendulum says, wait a minute, they're closer, and that changes some of our assumptions. That's what I meant by it.
Great. Okay, great answer, great presentation, and I'm afraid we've run out of time today. I'd like to thank Grady again for his informative presentation and insightful answers to the many, many questions. A special thanks to each of you for taking the time to attend and participate today. This webinar was recorded and will be available online in a few days at webinar.acm.org. You can find announcements on upcoming webinars and other ACM activities at learning.acm.org and acm.org. Also, please take the time to fill out the quick survey where you can suggest future topics or speakers which you'd like to see. On behalf of ACM, Grady Booch, and myself, Will Trace, thanks again for joining us. I hope you will join us again in the future. This concludes the webinar.